Welcome. This is the crypto lecture. There are three parts. In the first part, we trace the history of early ciphers, but first we want to define what cryptology is. Cryptology is the science of codes. We mainly focus on cryptography, the process of creating codes, and cryptoanalysis, the process of breaking them. There are other parts which are related, like error correcting codes or compression algorithms. The basic setup is to consider two players, called Anna and Bob, who want to interchange information in a secure way. Anna could be you, transferring some money to Bob, the bank. Eve, the eavesdropper, can see the ciphertext but shouldn't be able to read it, or even worse, change the text. So, for example, to take the money and have it diverted to his account. Why do we need secrets? There are many places where it is essential that we have secure communications. Here are a few. Of course, the obvious ones, like having health data private. Less obvious is that historically many conflicts were deflated by quiet diplomacy away from the spotlight, or that new exciting business ideas might need to grow and flourish first before being public. With transparency, a large competitor might just snatch the idea away and give it no chance to grow. The very early efforts in cryptography are in the dark. This is best illustrated with a Phaistos disk, which is believed to be 3,600 years old, made of clay, found in Crete, and which still remains a complete mystery. The nature of the symbols is not clear. Is it a cipher, or is it art, or just an alphabet? Here are both sides of that document. Some have suggested it might be even a hoax, but there is also no evidence for that. It appears that without more information, the secret of these symbols remains safe. Actually exciting. The disc is even featured on the front page of a book of Richard Mollin, by the way, a very good book. The first cipher we know of is the skittily. It is a simple device which the Greek poet Archilochus has described. Wrap a leather strip around a stick, then write on it. After taking it off, the message can no more be read. The earliest steps for cryptoanalysis has been done by Al-Kindi, who lived in the 9th century. He was the first to use statistical analysis to crack substitution ciphers. We look at these ciphers first. One of the simplest ciphers is obtained by just permuting the alphabet. Caesar is the first who is known having used this substitution cipher. He's also a famous pop hero. Here's an example. So shift the alphabet by 3 to the left. Actually, Caesar used to shift the alphabet by 3 to the right. Augustus, the nephew of Caesar, was a bit more lazy, even shifted it only 1 to the right. A special role plays rot 13, which rotates 13 to the left. It is special because if we apply it twice, we get back the plain text. This cipher is involutive. Here's an example. You can implement the cipher on a terminal. So my name is by-wire Xadi. Another famous example, which is of historical interest, is the @bash cipher. It just flips the alphabet around. According to Pickover, the cipher was used in the Old Testament, especially by the prophet Jeremiah. A more general substitution cipher allows for general permutations, not just reflections or translations of the alphabet. This gives much more possibilities. Still, all these ciphers are easy to break using statistical analysis. We mentioned Al-Kindi already. So here's an experiment. Let's look at the following text. It looks like gibberish. But now let's give you the frequencies of each letter appearing in the text. Now you just simply count. You know that F must stand for the letter E because F is the most frequent one. U must stand for the letter T because it's the second frequent one. This allows us to figure out the rest pretty quickly, and you will try that out in your homework. More sophisticated are polyalphabetic systems. They were introduced by monks in the Vatican, like Trithemius, who wrote the first printed book on cryptography. He's the first page of the book, and here a little bit larger. It's a gorgeous illustration, Trithemius. Inside the book we find a polyalphabetic cipher. The idea is to shift the alphabet after each step. This allows to break the frequency analysis. So here's an example. In this case, the first letter M goes to N, the second letter A goes to C because the alphabet has been shifted by 1, T goes to W because it has been shifted by 2, H to L, etc. Also, Leon Battista Alberti from Genoa was a pioneer. He introduced, for example, the Alberti disk, which makes the process of writing encrypted text more practical. A famous story illustrating why strong ciphers are important is the fate of Mary Queen of Scots. Her execution was prompted by the deciphering of a letter of hers, an encrypted letter. The drama involved Walsingham, the spymaster of Elizabeth. He could, with the help of a cryptology analyst, Philippes, decrypt a letter to Mary, to Babington, and seal her fate. In the movie Elizabeth of 1998, the plot is told in detail, even not quite following history. Geoffrey Rush plays the role of Walsingham, while Cate Blanchett is Elizabeth. The story is more accurately told in the book The Code Book by Simon Singh. So here is a scene from that movie. I have to cut it short. At last, let's mention the Pigpen cipher, which is supposedly used by Rosicrucian Brotherhood, Templars of Freemasons, or then the American Civil War. Here's an example. What does the message say? Yes, X marks the spot. So here are 3 books. The first one is Mollin, the most serious book of all these 3. I think it's the most entertaining, nicely written. And The Codebreaker, the third one, is the best illustrated. This is the end of part A. In this second part, we look at the story of the Enigma. It will start where we have left off, with polyalphabetic ciphers. First to the Vigenère cipher. It was actually discovered already by Giovanni Bellazzo. Cipher was used in the American Civil War. Here is a device from this time. It was used for a long time until the first part of the 20th century. One can even get some modern versions. Here's a picture showing one, but the principle is the same. You just change the alphabet, but you change the alphabet after each encoding. There's still a statistical analysis possible, but it's more complicated. This analysis has first been done by Charles Babbage, and a few years later by Friedrich Kasiski. Now to the Enigma. It looks like a typewriter. It has been patented first by Arthur Scherbius, a German electrical engineer. The machine was used in the Second World War. Code was eventually broken at Bletchley Park in England. It is a famous story told in a few movies. We'll look at 3 of them. The first is the movie Enigma from 2001, a Hollywood-type movie with a happy ending. More realistic is Breaking the Code from 1996, closer to the history. And the most recent one is the Imitation Game from 2014.
The Germans switched.
Computing devices played an important role in breaking the code. Here's a replica of the Enigma breaking machine, the bomb. Each wheel replicates one Enigma. Here's a historical picture. We will discuss the role and history of computing in the last lecture of this course. There's another scene from Enigma stressing the importance of these devices.
Mr. Jericho.
Another scene from the Imitation Game, but I cannot show too much here. Colossus was an early computer used for breaking codes, like encryptions done by the Lorentz Enigma machine. You see there are more rotors now, already 6 rotors, and the technology was used until the 80s of the 20th century. Here is a machine used in Russia, and here one in Switzerland. That one had 10 wheels already. I myself could once touch an Enigma at the AMS conference, and this is the end of part B. In this third part C, we look at public key cryptology. There will be a bit of number theory involved. The first part is the Diffie-Hellman key exchange mechanism. It solves the problem to share a common secret over an open channel. was done in 1976. Here's the mechanism in one slide. Anna and Bob want to establish a secret key which only they know. P is a fixed public prime, everybody knows that. A is a small number, public, also public, like A is equal to 2. And now Anna chooses a number x and Bob chooses a number y. So Anna can now compute a to the power x modulo pi, modulo p. This is the remainder when you divide by p. And Bob computes the remainder of a to the power y when you divide by p. So they can exchange capital X and capital Y over a public channel like the internet, and now both can form a number. Bob has just obtained capital X from Anna and knows Y, so he can form capital X to the Y, and Anna has got Y, capital Y from Bob, and can compute Y to the X. And these numbers are the same because both are a to the xy by the laws of exponentiation. This is a pretty cool setup, and Eve just knows the capital X, capital Y, and does not have access to the X and Y, doesn't have access to Z, so cannot find deduce the common secret which Anna and Bob have just obtained. So here's an example. So A is equal to 2, let's say take A equal to 2 and P is equal to 23, the prime. Anna chooses X equal to 5 and Bob chooses Y is equal to 7. So Anna can now form 2 to the 5 modulo 23, which is 9. And Bob can form 2 to the 7 modulo 23, which is 13. Now that's what is exchanged. So Anna has obtained 13 and can take this to the raise this to the power 5 and get 4. That's the Z. And also Bob can take the 9, having obtained it from Anna, raise it to the power 7, his number, and get the same number for 4. So they have now the common secret 4, and nobody else knows that secret. It turns out that Malcolm Williamson has found this a few years earlier. He's the internal memo that has remained secret for some time. It has been found at the GCHQ, the Government Communications Headquarters, or shortly Q branch. Next we come to RSA, a protocol developed by three: Ron Rivest, Adi Shamir, and Leonard Edelman. So here are the three at the time of their discovery. Also, this encryption depends on number theory. It solves a different problem, the problem to transmit information over an open channel. So here we have Bob and Anna. Bob has a text X, which he wants to transmit to Anna. Anna has chosen two primes, P and Q. She doesn't publish the primes, but publishes the product, PQ, and a small number, A. Now, Bob performs his text X to the power A modulo N. Take the remainder and you divide by N. And that's what he submits to Anna. Now Anna can compute the number B, which has the property that BA has remainder 1 modulo P minus 1 Q minus 1. She knows the primes P and Q and can do that. And so she can compute Y to the B. And that turns out to be X by theorem of Fermat, which we have seen before. It's a little bit a generalized form of the theorem we have seen in the number theory lecture. So she has now the text X. So here's an example. Bob has the secret message X equal to 4, which he wants to transmit to Anna. Anna publishes 21, so she knows 3 and 7, publishes only 21, and also takes the number A equal to 5. Now Y is just 4 to the 5 modulo 21, that's 16, and that is sent over. Anna can compute b equal to 5. B times a, 5 times 5 turns out to be just congruent to 1 modulo 12, and x cannot be computed. X is 16, coded text to the power 5, and Anna knows now the secret, plain text 4. So the RSA encryption also depends on number theory. Both depend on difficult problems in number theory. Diffie-Hellman depends on the discrete log problem. So it is a problem to compute the x when we know a to the x modulo p. And RSA depends on another difficult problem. It's the problem to factor in large integers. So if you know the product of two primes, you want to find the primes. So this problem of factoring integers is well studied and is studied all over the world. Here's a movie, Sneakers, where this problem appears and where some mathematician actually cracks the code and finds a way to factor that faster. And Edelman was a consultant in that movie. Robert Redford plays here. It's a great movie.
You seen anybody?
And this is the end of part C and the end of this lecture.